why a guitar? So what drove us to do this? I ask myself that every day. One thing I need to emphasize really is in Japan, how big trade shows are. They're a huge marketing tool over there. More so, I think, than here, I would say. Even a smaller trade show for engineers or engineering or even just variety, they can attract in a city like Nagoya, you can get 10,000 visitors a day going to these shows. So when they're on, everyone, you can't contact any of our customers because they've all gone to see the trade show. We were approached by the company at the time we were sharing an office with, called Hargreaves Vehicle Design, who are they're big into 3D printing, and they wanted a showpiece that they could put on their stand at a trade show. But their rules were they didn't want an automotive part, but they wanted something recognizable so anybody could see what it is, but not in a way they've ever seen it before. So hence recognizable shape in unrecognizable form. So from that, we started the journey of the guitars. And I want to emphasize that this is a journey. It's one that's not finished yet. I personally don't think we've reached the destination with what's possible with this. So if anybody has any ideas or things they want to see or anything like that, come and see me afterwards. We can have a chat. So the version 1 guitar was designed for 3D print. HVD have a very big PU 3D printer where you can just nicely fit the body of a guitar in. So they were like, oh, great. But at the time, it was just meant to just be just there, just to look at, just look pretty. We didn't really care about the noise, the sound of it. It was just to look nice. So obviously, optimizing for looks is a little bit difficult. The Genesis doesn't understand what looks good and what doesn't. So we added some basic stiffness cases and things like that. I'll explain those in a minute. And in terms of getting a design space, something to optimize, we needed something, reasonably beefy, give it Genesis some work to do. So I'm a personal fan of the traditional classic Telecaster designs. So, and usefully, it's a big chunk. So perfect design space. So in terms of setting up a model, chose a little selection of loads, mostly G loading, so representing the loads of, someone playing a guitar on a stage and jumping and the guitar dropping on the strap. Obviously string preload, because nobody wants their guitar to snap in half when they tune it, because that would be embarrassing. Also loading for it being sat on your knee, playing it. Obviously you've got the weight of the neck overhanging and things like that. And I did include the modal load case, mainly just to ensure bits aren't falling off more than anything. And I used just a very traditional topology optimization setup. So 30% mass fraction, so keep 30% of your design space and minimize the strain energy of all the load cases, maximize the first mode. So the traditional setup, stiff as possible for this fixed mass. And product placement time, I used GRM Design Toolkit's STL hex mesh to make the mesh. So this wasn't a very well-paid project at all. So getting a model up and running quickly, getting it meshed and bish bash bosh was what we needed, and the STL to hex mesh fitted the bill perfectly. So this is the version 1. So as you can see, it's a very skeletal design. So whilst you could make this with other methods, you could cast it, you could CNC it out of a chunk of material. Doing either of those things would be quite difficult. It's a lot of surface area to deal with, and finishing it would be tricky. So in terms of a design for 3D print, it kind of fitted the bill. And to get this skeletal design, I used a lot of max size constraints in Genesis to control how big the members got. Unfortunately, at the time of the trade show, just before when we were due to have the manufacture done, HUD received a load of properly paid 3D printing work. So the 3D printer was in use constantly for about a month, so they never got a chance to manufacture it. And then COVID hit, so there were no trade shows for a couple of years. So we never got actually a real chance to see what this design could do. However, that's not the end of the story, of course. So we decided, GRM, we were going to exhibit at DMS Nagoya in 2022. And we, of course, needed a showpiece, something to show on our stand, something to capture imagination, bring in people to talk to us. We're a small company, we don't have a whole car we can have that people are going to go, ooh. So I needed something eye-catching, people to recognize. And I spoke to HVD and said, can we use that guitar that we did for you? And they were like, yeah, go for it. That's fine. So we also decided to, if we're going to make a guitar, we get, some professionals on board. So we had decided to enlist the help of a company called Eugene, who they're specialists in making prototypes, mostly, metal parts, plastic parts, things like that. But conveniently, they also have a small division that does guitars. And I'll explain a little bit in a minute. But they had, so we went to them, we had a nice meeting, and their feedback on our original design is, yeah, looks really good, but we've made 3D printed guitars before, and they sound rubbish. The material doesn't resonate well because of the layering of the 3D printing and the way it works. So yeah, they're light and interesting, but they don't sound any good. So if you're going to do this properly, we want to make something that looks good. We want, to be able to proudly put our name on it. So let's make it out of wood, like proper tone wood, in this case maple. So obviously this requires a little bit more thought. I'll just quickly introduce UID or UID. They say UID, it's fine. They're a subsidiary of this Eugene prototype company, and their main business is making customized guitars for discerning guitarists. So guitarists who want something completely unique, they will go to Eugene, and Eugene will listen to their requests and come up with whatever design they're after. I've got catalogues out there, you can feel free to come and have a look. There's some very crazy designs. Whether they sound good or not, well, that's up to the ear of the beholder. They also have on their staff, they have ex-PRS luthiers, so they really do know what they're doing in terms of making guitars. And an extra bonus for us, they were local. They're only half an hour up the road. Happy days. So, how do we go from doing a simple guitar for 3D prints to doing a wooden one? And also start to think about, how is it going to sound? Well, I won't go into too much detail, but we updated the model build of the project. We included some frequency response type conditions, which I'll cover in a minute. Obviously, we changed the material in Genesis to represent maple, because not doing so would be silly. And we were told by Eugene, it's like, yeah, we could cut that design out using our CNC, but what a waste. This maple's been aging and curing for 30 years. It's like, we want to make the best use of it. So they were like, can you change it so that we've got more surface area to show off this wood? So we were like, yeah, all right, we'll give it a go. Now, normally you wouldn't use manufacturing constraints for that, but we decided that the way to do this would be to play with the manufacturing constraints a bit to give us the design we were looking for. And this is not a computational idea, it's an aesthetic idea. So there was a little bit of trial and error. In terms of the frequency response, this is the concept I came up with. So a little bit of, this is about as theoretical as I want to get, I think. Electric guitar, of course, most of the way the sound comes from an electric guitar is it comes from the pickups. You've got, in a Telecaster, you've got the one at the bridge and the one at the neck. And the way the sound comes out is you've got the string vibrating in the magnetic field of the pickup. This then gets picked up as a vibration through the jack, out to your amplifier, and then you get big noise, melting ears, melting faces, everyone's a winner. However, if you make the guitar body lighter, take the material away, you're going to make it bend, you're going to change the bending mode, you're going to make it softer. So then as you're exciting the structure by playing the strings, your structure is going to be bending, which will change the tolerance between the string and the pickup. And I don't know how knowledgeable people are about, but guitarists spend, some guitarists will do the setup themselves. They talk about setting up the gaps between the pickups and the string to get the best tone out of their guitar. And of course, if you've got a guitar body that's really soft, you can do all the setup you want, but as you play it, that tolerance between the string and the pickup is going to be changing all the time. So you're going to get slightly variable tonal output based on what you're playing. So I decided, as a start of a 10 on this journey, I'm going to use frequency response optimization to minimize this detrimental effect of making a guitar lighter. So I think the last bit of product placement. This is, so recently, in recent years, Genesis has really come on for its frequency response optimization. It's now much easier to do than it used to be. I think one of the reasons I didn't do much of it at all for the first prototype is at the time, it was doable in Genesis, but setting it up was a little bit whereas now it's dead simple, which is really good. And you can do things like you can minimize the peak response. You can control the frequency of the first peak of the response or the maximum peak of the response. You can do the anti-peak if that's what you need to do. And you can do a constraint for this, so don't go above this value, or you can do it as an objective, so minimize or maximize. And obviously this allows you to control acoustic responses or vibration and resonance for, well, anything. In this case, our guitar. So moving on, we have a bit of trial and error. So this is just to show that, the first thing out the gate is not always what you need, really. So the first design on the left, you can see, it's worked, it looks interesting, but it's got some very spindly bits. Obviously, you cut those out of a piece of maple. As soon as you nudge it with anything, it's going to, whilst the strain energy might be low in the analysis, in real life, it's not going to work. The one in the middle is much better for that. We updated a non-design region to, provide the covers for the cables and things like that, and optimize that, which, could have worked. But one thing we did think is it's a bit too chunky, a bit too much of that material left. It didn't really excite us. There was no wow factor to it. The one on the right, again, similar. And what we're doing here really is just tuning some of the parameters of the manufacturing constraints, tuning some of the weight factors of the load cases and things like that. It was a little bit of experimenting. It was kind of in the background while I was doing the proper work for companies. Obviously, some of these designs will have better sound, some will have better structural, but we're trying to seek that balance between the good performance and the good, the aesthetics of it. And our final results, we came up with this, which is this design that sat on the stage next to me. We have that greater surface area compared to that first 3D print prototype, which is what we wanted. All the required parts on a guitar, obviously the bridge, the other plates, they're all well supported, so they're not going to start flapping around as you play it. So we showed this design to Eugene and said, what do you think of this? And they were like, yeah, we'll give that a go. Obviously from the optimization, there's a couple of extra bits that got added. There's a cable channel and things like that because there wasn't any routing for some wiring. But other than that, it's pretty much almost direct from the optimization to some CAD. But what about let's talk about this bridge response. So how does this get affected? So the colors are probably a little bit difficult to see from back there. But here we have black, which is a baseline, which way is it? Black is a baseline guitar, so pre-optimization, standard guitar. Blue is the effect of making the body a 30% mass, so making that lightweight, but just an isotropic chunk of light, airy wood, maybe balsa wood, for example. And then red is the optimized design. We can see here how lightweight in the guitar massively increases. On the left, this is the neck pickup. So this is the displacements of this pickup here as through the frequency range. And the coloured bands are coloured according to what notes you would typically use for each of the 6 strings. I can see here how lowering the mass of the guitar hugely increases this peak resonance of the neck pickup on the blue line. And we can see how optimizing the placements of this light mass and making it solid in the right areas greatly reduces this frequency peak. And on the bridge pickup, it's a little bit more complicated because the bridge pickup's actually bolted to the bridge. So you've not just got the body resonance, you've got the bridge as well. But across the board, we've actually got quite a good, nice level response. And we've actually, for the top string at about 300 hertz, we've actually got a better, lower, more stable response, less displacement of the pickup relative to the string. We've actually got a better than a standard normal guitar, which is what we would hope to achieve. So manufacture, the whole thing is CNC cut from maple. It's, then hand finished by the luthiers at Eugene. For this is the first prototype that was ever done. All the other parts, the bridge, the plates, everything, all just bought off the shelf. So just to put a guitar together that works. This is the one of a kind, and this one's got a clear PU finish. I think it was PU finish. I don't remember. Yes, but the skill of the manufacturer is really evident to see, and we were really pleased with how it came out. Other people we've seen who are like, we couldn't do that. So, well, go to Eugene, they can. So the first prototype, this guitar was delivered to us at Eugene's offices. You can see, again, this is still peak COVID time. We're still all masked up. And I think it shows off really well what we were able to do with some of the vibration optimization, but also what Eugene were able to do with their manufacturing. And the initial feedback was good from Eugene. But of course, it doesn't really matter what they think. They made it. They're going to give us good feedback. What did people at trade shows think? So here we have our good our good friend Kurokawa-san, who is actually the designer of the chair as well, decided to come and visit us at DMS Nagoya. The feedback from the pro guitarists at Eugene is that this guitar has very, very fast response. So the timing between playing the strings and getting the signal to the amp is very fast, and that's a really prized quality for guitarists who are going to play on a stage. Because obviously the stage, you've already got effects and cables and the amp all adding lag to your signal chain. If the guitar's adding extra lag, then it becomes more difficult to play live. So having a guitar with fast response is a very key feature, and that response is coming from the stability of the pickups relative to the strings as it's been played. Other feedback of the empirical variety, the subjective variety, it looks cool. Somebody came up to me earlier and said, that's the coolest thing I've ever seen. So I was like, yeah, thank you. Another company who was exhibiting at DMS Nagoya also had a guitar on show. This was a CNC aluminium guitar. And they saw ours and said, wish our company could do that. It's like, thank you. Well, come to us and we'll help you do that. Which I'm still waiting for the contact from them, unfortunately. The most common feedback I had was, let me know when you make a bass. So it seems that Japan has more bassists than guitarists, but hey-ho. So what's next? We've got this thing. What's next? Well, Eugene and UID decided that they want to make an exclusive run of 10 of these guitars as a high-end product to show off, this combination of the technology and traditional craftsmanship. There's a limited run of 10 available. If you have 1.8 million yen sitting in your pocket, that's about £15,000. Yeah, let me know. We can talk business. However, from Prototype 1, UID have made their own customizations to make it even more bespoke, even nicer. It's got a bespoke case. All of the plates have been replaced with custom titanium ones, including even the machine heads. And they've got a nice satin finish, which at first I saw it, I didn't like it, but having played it a little bit more, I do quite like it now. And of course, each one is adorned with the most important parts of the guitar, approved by GRM Consulting. It surely adds 50% to the value. But of course, to sell a premium product, you can't just go off subjective feedback. We need numbers. So we, through contacts at Eugene, we arranged an afternoon in the anechoic chambers at Kawai Instruments. Kawai, of course, well known for their pianos and keyboards. So the objective was to let's have a guitar showdown. So we took Prototype 1, we took the first manufactured sample down to Kawai's research and development facility in Shizuoka, and we took a few other guitars as well, and did some testing. The testing looked like this. We strapped the guitar onto a stand. We've got a microphone in there to record the resonance of the body acoustically. We've got piezoelectric transducers on the body to get the body vibrations. And of course, we're also recording the line input from the guitar so that we can understand, is that response really fast? Or is it just somebody's ears thinking that it is? So we tested this. We tested 3 other guitars and the first manufacturing prototype. And across the board, we can see the 2 optimized guitars are the 2 bars on the right. Across the board, we've got really high levels of output. We've got really long sustain compared to other guitars. And yes, the response is fast. I hope that's readable from back there. But Taguchi-san, the engineer at Kawai, he says the Mana guitar, this is known as the Mana guitar, has a good body sound from bass to treble. It has stable vibrations and a character that produces high harmonics well. So positive feedback from a professional, instrument test engineer. So I was quite pleased with that. Interesting point to note, though, is how in yellow is this prototype here, and the blue is the optimized guitar with titanium plates. And you can see how we actually have higher output levels, higher resonance on this one. And I think this is down to the plates being stainless instead of titanium, just changing those body vibrations. And of course, when you've done testing, of course, the next step is to go back to your CE. Does your CE make sense? And this is where we're into the realms of, I'm still working on this. So I can't give a final answer. The low frequency peaks in terms of our frequency curve, our low frequency responses in Genesis look very good. So below a couple of 100 hertz. As we get into the higher frequencies, we start to see some differences between the test and what we see in the analysis. So that's something I'm working on. I think it could be more down to some of the damping parameters of the materials and things like that. So my next port of call is to get some offcuts of the maple to try and do some empirical testing of just the material itself and make sure that our material we're using in the analysis is all what we need. And what's next in terms of developing guitars and instruments? Obviously, I enjoy it. It's good fun. So, well, as I've just mentioned, we're going to try and get the correlation there, get it so that we can accurately say our analysis matches what we saw in test. We need to also investigate what other parameters we could consider in an optimization. One thing I regret not considering in this particular guitar is the center of gravity. This guitar has a tendency when you play it to try and slip to a horizontal position, to a more low position, just because of the balance of the CFG is slightly off compared to a normal guitar. So I would try and consider the center of gravity in a future optimization. Other things to consider, maybe maybe enhance or dampen specific frequency ranges. So a guitarist who wants a really bass-heavy guitar could just say to us, I want that. And we can go, right, here's your body shape. Boosh. And other body shapes. This is a Telecaster. What about a Les Paul? A Strat? A Gibson Flying V type shape? And other instruments. I've already mentioned bass. I'm personally a cellist. I've been playing cello for more than 20 years. So I'd like a lighter cello that sounds good. So, there are lots of different avenues to explore with this. But first we need to shift the 10 of these that we've got lying around. So, yeah. And finally from me, so I think just about my time, I think. Finally from me, I'd like to acknowledge a few people. I'd like to acknowledge Ito-san from Eugene, who I did invite, and unfortunately he was unable to make it over. He was very good in driving us along the path to getting this thing made. Taguchi-san from Kawai, who let us play in his test lab for an afternoon. They don't normally let people in the test labs at Kawai, so that's why there were no photos inside the lab. It's all very, they've got their own configurations. And I'd also like to thank Kyle, our own Kyle, who was a very receptive sounding board for some of my crazy ideas and gave me some really good feedback and technical leads. So thank you to him. And thank you to all of you for listening to him.